We talked a lot about the crystallographic systems, the cubic, the tetragonal, the orthorhombic, the monoclinic, the triclinic, the hexagonal, and the rhombohedral, right? And we know exactly what the conditions were. And we also warned that these lines or the representations as cubes or parallelepipeds is only for visual thing. In reality, the atoms are just touching each other. So we are just drawing imaginary lines to understand the symmetry. Okay, so we have to keep that in mind all the time. We also talked about the effective number of atoms. We also talked about primitive, body-centered, face-centered, and side-centered cells. And you should be very familiar with all of them now by now, but if you have any questions, this is a good time to ask. So as time was running out last lecture, we just talked about the effective number of atoms in simple cubic, which is primitive, is 1, body-centered is 2, face-centered is 4, and side-centered is again 2. All right. And then we looked at how to find the stoichiometry of any compound just by looking at the unit cell and the location of the atoms within the unit cell. We gave some examples such as barium titanate, I believe, and we gave some examples of niobium telluride, Nb3Te. So that's where we were last time. I just wanted to pause for a second to see if you have any questions on those. Anything that was not clear. I hope you're all following the lectures because you're not learning this for this class, but you're learning for your life. So please keep that in mind. It's just not by not asking questions, by silently sitting there, and suddenly in the exam, we never expected this. We didn't know that this is what we are expected to know. I will not allow that kind of excuses anymore because I want you to participate in the class as actively as you can. So the next thing that we are going to do now is, so once we know the arrangement of cells, uh, can we relate the microscopic arrangement of the atoms in a unit cell to macroscopic properties? So microscopic arrangement is, in a small space, the atoms are located. How would that change the macroscopic properties? So we'll talk about the density of a metal. How does that get affected by the arrangement of atoms? So I'm going to write a small problem on the board. All right. So, and we'll try to find out the mystery metal that has these properties. So the way we start is an unknown metal is found to adopt a face-centered cell with a side of 0.556 nanometers. That's information given to you. And the density of the metal is found to be 1.54 grams per cubic centimeter. My question then is, based on this data, find the atomic weight of this metal. And once you find the atomic weight, atomic mass, you should be able to identify, because different metals have different atomic weights, right? Sodium has 23, rubidium has 80. So every metal has its own atomic weight. So once you know the atomic weight, you can go back to the periodic table and be able to identify what the metal might be. So in some multiple choice questions, sometimes we'll ask you a question like this and give you 4 or 5 choices, and we will say, pick up the right answer. Okay. So how do we go about this? Any thoughts on the class, from the class? We know the density, we know the side, and we also know that this is a face-centered cubic. So how do we approach solving this problem?
Should we find the volume of the cube first?
Wonderful. So what do we do with the volume of the cube then? What's my next step?
We can use the density formula to calculate the mass.
Okay, wonderful. We are in the right roadmap. So once you find the volume of the unit cell, because this is cubic, and if I know the side of the cube, then I know the cube of that side is the volume of the cube. So once we know the volume and density, we can find the mass. What do we do next? If I know the weight of the unit cell, how would that give me the atomic weight of the metal?
You would have to take into account the face-centered aspect of it,
Yes.
and how many molecules or how many atoms that has.
So if you look at a face-centered cube, right, something like that I'm holding here, how many effective number of atoms face-centered cube has?
For one
4.
side, I guess you could look at, it would be 5.
We already derived, right? The effective number of atoms in a face-centered cell is 4. Corners contribute 1/8, face centers contribute 1/2. So 8 times 1/8 plus 6 times 1/2 makes it 4. So whatever weight that we got for the unit cell, that is the weight of 4 atoms, right? If I know the weight of 4 atoms, I can find weight of 1 atom and then multiply that by the Avogadro's number to find the atomic weight of that metal. Am I making sense here?
Yeah.
So that is what the roadmap is. So whenever you do problems of this type, the first thing is we need to have a blueprint or a roadmap. How would you like to proceed? And once you have the roadmap, then the calculations are pretty straightforward. So the thing that we need to do now is the volume. You got to pay attention to the units here, folks. Okay, because our density is in cubic centimeters and our metric for the side of the cube is in nanometers. Am I making sense? So at some point you have to come to the reality, and then we got to find out, make sure that we are comparing apples to apples. A lot of times students, in their rush to finish the problem, will forget about the fact that they have different units and then keep scratching their head. Why didn't they get the correct answer? So the devil in these problems is in the details. It's very important to keep all the numbers straight. So the volume then is going to be the side of the cube. So a cubed, which will then say 0.556. That's in nanometers. And we know 10 to the negative 9 meters is a nanometer. So 10 to the negative 9 meters, 1 nanometer cube. When you do that, the number comes to about 1.719 times 10 to the negative 28 cubic meters. That is our volume. Now we got to convert this volume into the mass because I know the density. Okay, so the mass is volume times density. So because I know the density is 1.54 grams per cubic centimeter, however, my volume is in cubic meters, so I need to change my cubic centimeters to cubic meters. So for that, I will use 10 to the 6 cubic centimeters is 1 cubic meter, because 1 meter is 10 to the 200 centimeters, right? So that's where the cube, when you cube the 100, you get 10 to the 6. So that will be the thing. And then we have the volume, which is 1.719 times 10 to the negative 28 cubic meters. So if you look at the arrangement, cubic meters cancel and meters will cancel, and the answer will be in grams. So that works out to be 6.618 times 10 to the negative 23 grams. No, that's not correct. That comes out to, sorry, let me reword this. That comes out as 2.647 times 10 to the negative 22 grams. That's the mass of the unit cell. That mass, now we know, corresponds to 4 atoms. So if you want to know the mass of a single atom, you need to divide this by 4 to get the mass of a single atom, which is what corresponds to 6.618 times 10 to the negative 23 grams. Am I making sense here, folks? That is the mass of a single atom. So if you want to know the atomic weight, you take the mass of a single atom and multiply that by the Avogadro's number, which is 6.022 times 10 to the 23. When you multiply that, you get the atomic weight, and the atomic weight comes to about 39.84 grams per mole. I'll give you 1 minute to digest all the stuff here.
Could you move the camera down a little bit? Or write the atomic weight? Okay, that's good. Thank you.
Is that better? Can you see 39.84? So the answer to this problem is 39.84 grams per mole. So if I give you some choices here, potassium, rubidium, bismuth, calcium, thallium. Choice A, B, C, D, and E. What will be your answer now for this problem? You have to go back to your periodic table, which you will have unlimited access during the exam. Now that you know your atomic weight is close to about 40, which metal has an atomic number close to 40?
Would it be potassium?
Potassium, what is the value?
A.
No, what is the atomic weight?
Oh, 39.
39. What's the atomic weight of calcium?
I think it's calcium. It's 40.
40, right? So this
Yeah.
one is close to 40 than 39. So the answer should be
D.
D, calcium. these calculations are really precise to the fourth decimal. So to 3 significant figures, right? So if you write to 3 significant figures, that's 39.8, which is closer to calcium than to potassium. So pick up that answer. So if you pick up potassium, that we get a partial credit, but for calcium, you get a full credit. Again, I told you the devil is in the details.
Could you explain why did you divide by 4 again?
Okay, because this 2.647 times 10 to the negative 22 is the mass of the unit cell. Because it's a face-centered cubic system, that mass corresponds effectively to mass of 4 atoms. So if you want to find the mass of a single atom, then you divide that by the 4 to get the mass of a single atom. That comes to 6.1618 times 10 to the negative 23. You multiply that, which is the mass of a single atom, by the Avogadro's number to get the atomic weight.
Yeah, is it because the Z effect for FCC is 4?
That's correct. If this problem were to be a body-centered cube, right?
Yeah, that's 2 then, the Z effect.
Then
Yeah.
that's going to be 2. You
Yeah.
divide that by 2. If it's a simple cube, you divide that by 1. If it is a side-centered cube, you divide that by 2. So you have lots of variations here. But no matter what they ask you, once you understand the basic principles, the rest is all just mathematical manipulation. Good questions. Are we making sense here, folks? Sometimes I may ask a question entirely differently. I will give you, this is a calcium metal, and it has a density of 1.54 grams per cubic centimeter, and it adopts FCC center, FCC cell. So I'll ask you to go back and calculate what will be the side of the cube. Let's be able to solve for the third one. In here, we're talking about solve for the atomic weight, but if you already know the identity of the metal, then you can, reconstruct the entire roadmap and be able to calculate the side of the cell, and you will come to 0.556 nanometers. That's the beauty of solid-state chemistry. Am I making sense here? My next question I will ask you is, now that we have this information, the side of the cube is 0.556 nanometers, can we find the radius of calcium atom? All right, so for that, we need to do a little bit of geometry here of the face-centered cells, which is what I'm going to show you. But before I ask you, are there any questions on this problem so far? Okay? If you ask me questions the day before the exam, that will be too late, because that will be too much of a thing to learn in 24 hours. And some of these questions that I'm going to ask will not be on the check, because very rarely people teach solid-state chemistry. It's not that it's not important, it is just that there are very few people trained in this area. So majority of them use coordination complexes and skip this topic. It's very important for industrial applications. So please keep paying good attention. So the next thing is, calcium adopts FCC lattice type with a side of 0.556 nanometers. Find the radius of calcium. Any thoughts on this? Any ideas, folks? Let me show you again the face-centered cell here. Right? In a face-centered cell, the atoms are touching along the face diagonal. So if you draw the face-centered cell, for clarity, I will just only show one face. So you have atom at the corner, atom at the center of the face, and atom at the corner. So that diagonal length corresponds to R plus R plus R plus R. So 4R is the face diagonal. I already know the length of this is 0.556 nanometers. So what should be the length of the face diagonal then? If the atoms are touching along the face, yes.
0.556 times, use like the 45-degree angle triangle to find it.
Yeah, but so if this is A and that is A, right? That's a rectangle right there. So if you're now looking at the hypotenuse of the rectangle,
Root 2a. Root 2a.
root 2A, that's correct. So 4R equals square root 2 times A. So R, which is the radius now, will be square root 2 over 4 times A. So in this case, it will be square root of 2 times 4 times 0.556 nanometers. Can anyone quickly enter this value in the calculator and tell me what the answer is?
Point 196.
Hmm?
0.196.
196?
Yeah.
I want somebody else to second this answer. Do the calculation. You have a calculator next to you.
I got the same.
You got the same answer. So that's the correct answer. 0.196 nanometers is the radius of the calcium atom. Isn't it wonderful? Okay, what happens if I have a body center? The problem here, and change the metal from calcium to cobalt, and it adopts BCC lattice with a side of 0.556. Find the radius of cobalt. Okay, so now I have a different situation here. I have atoms at the corners. We all know what a body-centered cube look like. So we have atoms in the corners. Of course, they're touching, and I have one atom in the middle of the body. So for those of you who would like to have a picture here, this is how it looks like. So you have blue atoms on the corners of the cube and one located right in the middle of the cube. All right. Now I'm asking you, if I know the length of this cube, what will be the radius? Cobalt atom. Now, unlike face-centered cube, in the body-centered cube, the atoms are touching along what we call body diagonal, not face diagonal. So one corner to the front corner here. So if you look at that line, that will be the length, which will be equal to 4r, because there are r, 2r, and another r. So total of 4r. That will be equal to what? What is the length of the body diagonal if the side is A?
Under of 3 times A.
Hmm?
Under of the 3 times A.
You mean square root?
Yeah.
That's correct. That will be square root 3 times A. But face diagonal is square root 2 times A, and body diagonals are longer for a cube. So if you now look at the body diagonals, just to give you a picture here, I'm looking at one atom, third one, and the other one here. If you can see all 3 atoms, 1, 2, and 3, that's the total length body diagonal. That will be square root 3 times A. So the radius of an atom then becomes square root 3 over 4 times A. So the radius of this one will be square root 3 over 4 times 0.556 nanometers. So what will be the radius here? Can anyone quickly calculate and tell me what the value
I
is?
got 0.241 nanometers.
0.241.
Yeah, I got that as well.
I need a second on this. Can I have a second person justify this answer?
Yeah, I got
Yeah,
the same.
I got the same.
Oh, most of you got the same. That's correct. So this is 0.241. Look at how things change when the type of crystal lattice that they adopt is different. Am I making sense here, folks? Questions?
I was just wondering, where were you getting the 4 from for 4R?
4r, if you look at this, right? If you look at the corner atom, it contributes only half of its radius here. You can imagine these are all touching here, okay? So along the body diagonal, the atoms are touching here like this. So that's your length of your body diagonal. If you can see the picture here that I'm showing. So that's an R. There is another R, and an R. So if you add all of them, that will be 4R. That will be the length of the body diagonal in terms of the radius of the atom.
Okay, thank you.
That makes sense? Great. Other questions? My next question is, we know the atoms are touching. So if you were to look at a face-centered cube, imagine all the atoms are touching. The only reason I separated them is because I want to see a clarity, but in reality, all these atoms are so big, they are touching each other. They are like spheres. So when these spheres touch each other, there is always small empty space inside. All right, so we want to know how efficiently the atoms are packed in a face-centered cell. Okay. All right, so we'll try to see how we can do this. Let's assume the radius of an atom is R and side of the cube is A. So let's talk about a face-centered cube. So there are atoms. Again, I'm going to write them. You can physically imagine these atoms are touching along the face diagonal. They're all stacked up in that direction. Good. So if the side of the cube is A and the radius of an atom is R, how would we find the fractional empty space? Forget about A and R. If you have a cube like this and you want to know what fraction of the space is occupied by the atoms if they're touching, what exactly would you do? You need to know the total volume of the cube and subtract from that the volume occupied by the atoms divided by the volume of the cube. So the fractional occupancy, FO, is volume of the cube minus volume of atoms divided by volume of the cube. All right. So in here, the fractional occupancy will be A cubed minus, if the radius is R of an atom, what is the effective volume occupied by all the atoms in a face-centered cube?
4/3 pi r cube.
4/3 pi r cube is the volume of one atom, right?
Yeah.
How many effective number of atoms we have in the face-centered cell? What did we say? Face-centered cell, the
Was it
effective
4?
number of atoms. Hmm?
4.
4, very good. So I have 4 atoms and each atom has 4/3 pi r cubed. That will be the total volume occupied by the atoms. This is the total space available in the cube, and that is the total volume occupied by the atoms divided by A cube. That will be the fractional empty space. That's the total space, that is the occupied space. The difference will give you the empty space divided by A cubed. But we already know the relationship between A and R, right? For a face-centered cube, how are they related? The atoms are touching along the face diagonal. So we said square root 2 of A equals 4R, correct? That makes sense? So we can say A equals 4 over square root 2 times R. So if you now take that value, plug it in this equation for A, can you all see this on the board? If for some reason, if something is not clear, not visible, let me know. So when you do that, it becomes, let me come back here and do this. So this is our A, so that makes it 4 over square root 2R cube minus 16 over 3 pi r cubed divided by 4 over square root 2R cubed. Can you all see that? There is an R cube, there's an R cube, and there is an R cube here, right? So simple math tells us that we can cancel the R's now. So this now simply 4 over square root 2 cube minus 16/3 pi divided by 4 over square root 2 cube. Can anyone tell me what that value is? Do your math slowly, because I want everyone to get convinced about these empty spaces. You need to calculate independently 16/3 pi, 4 over square root cube divided by 4 over square root cube. When I put questions like this in the board, it gives me an idea about how much of class participation I'm seeing.
Chari,
Yes,
can you move the camera down just a little bit? I can't see the
Sure.
bottom.
okay.
Thank you. That's much better.
Is that better?
Much. Thank you.
Thank you, okay. Please speak up because I can't see what you're seeing on your device. So I'm always willing to adjust my cameras. See value.
I'm not sure if I'm right, but I got 0.260.
Same.
Other people,
I got the same thing.
you got the same thing. You got 2-1, you're absolutely correct. The fractional occupancy is only 0.26, which means 26% of the space is empty in this face-centered cubic structure. Does that space, that number 26%, depend on the size of the atom?
It shouldn't.
It should not. Why? Because we
Could.
cancel the radius, right?
Right.
No matter what the radius is, whether you're dealing with grapes, small atoms, or pineapples, or watermelons, it doesn't matter. If you arrange them in the face-centered cubic structure, the fractional empty space is 26%. That means your occupancy is only 74%. You see how I'm playing with the words here? The fractional empty space is 26% space is empty, but then occupancy is 74%. Now, let me tell you one thing, very important. You can never have an efficiency greater than 74%, no matter how you arrange the atoms. This is the most efficient packing you can ever have. But still, the 26% empty space, that is the real estate that is vacant, right? I can do a lot of chemistry in that one. I can insert smaller atoms into the structures. I can change the properties. I can change the physics. I can change the chemistry, the engineering properties. I can put a little bit of carbon, small atoms into this space and make them pack a little bit more. That's how you strengthen the steel, by putting small amounts of carbon into it. That means you improve the packing efficiency. So a lot of design aspects of the materials properties, such as the strength, the conductivities, the dielectric constants, a lot of properties can be altered by utilizing the small amount of space that you have, 26%. Am I making sense here, folks?
Yeah.
Good. Now I'm going to pose, what if I have a body-centered cube? What is the packing efficiency of that? So we'll now draw a body-centered cube. When they imagine the atoms are touching, they are touching along the body diagonal. If A is the side, R is the radius, what will be the fractional occupancy of this? So again, volume of the cube minus how many effective number of atoms we have in a body-centered cube?
Two.
Two.
So 2 times 4/3 pi r cubed. That's the volume of the atom divided by a cube.
Professor,
Yes.
the top of the board is a little cut off.
Oh, I'm sorry. It's, my computer is so slow. Can you see it now?
Yeah, that's good. Thanks.
So copy it. All right. So what do we now do? What is the relationship between A and R in a body-centered cube? How is the A, the side of the cube, related to R, which is the radius of the atom? We did this before.
Would you just replace the 4 with the 2 in the last example?
No, the length here still is 4r.
No.
But-
Okay.
So what is the length of the body diagonal, not the face diagonal, but the body diagonal here in terms of A? What did we say before? Four R. Didn't we say 4r equals square root 3 times A? That's the length of the body diagonal. Right, so A then equals 4r square root 3 times R. So now you take this, plug it in that equation. So the fractional occupancy now becomes A cubed, which is 4r square root 3r cubed minus 2 times 4/3 pi r cubed divided by 4r square root 3r cubed. Again, if you look at the common factor r, the r gets cancelled. So you have now 4r square root 3 cubed minus 2 times 4/3 pi divided by 4r square root 3 cubed. Can anyone please do the calculation? Tell me what this value is.
Is it 0.32?
Hmm?
Is it 0.32?
That's what I got.
You are absolutely correct. So, in body-centered cube, we have 32% empty space, only 68% is occupied. Am I making sense? So which one is an efficient packing system? Face-centered or body-centered?
Face-centered.
Face-centered has a better occupancy, more 74%, compared to 68% that you see for the body-centered cube. So imagine if I have a body-centered cube and if I apply very high pressure, what do you think will happen to this body-centered cube? You try to apply pressure, you're going to squeeze the atoms together. So would you expect a transformation, a phase transformation in this? Clearly, when you apply pressure, right, the system will go in a way to reduce its empty space. So from a body center, we have 32% empty space. Phase center is only 24. So it will go from BCC to FCC. So whenever you see pressure-induced phase transitions, it kind of gives you an idea why the nature behaves the way it does. Am I making sense here? Let's now see what happens if I were to have a simple cube. Simple cube is basically primitive. Atoms only at the corners, nowhere else. Let's see A, and the atoms touch along the edge. That is your A and R and R.
Professor, we can see the top of the board.
I'm sorry. Okay, can you see that?
Yeah, I can see it now.
Good, yeah. We're going to have a recording of this. Will be available in about a day or two. Both this lecture and the lecture we have had last week, we're going to put that one. Okay, so what do you think fractional occupancy for a simple cubic structure then? Now that I showed you exactly how they're touching, and I showed you how to do this calculations, fractional occupancy will be A cubed minus, how many effective number of atoms we have here in a primitive cubic system?
1.
1. So it's only 4/3 pi r cubed divided by A cubed. And A, if they're touching on the sides, what is the relationship between A and R then? A equals what? Is it 4R or 2R? You can unmute yourself and answer.
2R?
Thank you. I don't know why this is such a difficult question, because you're physically looking at two atoms touching each other, and the distance between the radii is your length, because they're touching along the edge of the cube. So A equals to R. So you can now plug in and tell me what the fractional occupancy is. You can do a quick calculation now. So instead of A, we're going to have 2R and again 2R here. And the R, all cubes get cancelled. So that will be 2 cube minus 4/3 pi divided by 2 cube.
I got 0.48.
So that's your empty space, 0.48, and the occupancy is only 52%. So this is a lousiest way of packing an atom. So that's the reason why many solids, many elemental solids in the periodic table do not have this structure except for one crazy element by name polonium. we still don't know why that element is so stupid to adopt primitive cubic system. There may be other forces, but in general, majority of the structures that you see are hexagonal close packing, cubic close packing, or body centered. Very rarely do you see a primitive cube except polonium. Am I making sense here? Questions up to this point? Anything that's not clear? Okay. The next thing we're going to talk about crystallographic planes. Before I continue, I would like to inform all of you that coming Thursday, we will not have in-person lecture, but I will upload videos of my lecture. So Thursday, around the same time, you will be viewing the same lectures on your Canvas. So please make sure that you watch those videos. That will be again in the solid state chemistry. So we'll not have in-person meeting, but we'll continue in-person meeting next Tuesday again. But this Thursday, it will be all remote, asynchronous remote. Okay, let's now look at crystallographic planes, which are basically given by what we call Miller indices. A Miller indices is a mathematical phenomena. In fact, the description of crystallographic planes precedes almost a century compared to solid state chemistry. So people in the Greek philosophy, they understood exactly what cubes are, and then they developed a lot of systems to understand the cubes. So for example, if I have a cube like this, I have an atom in the middle. But if I have a cube like this, face-centered cube, I don't have atoms in the middle. So how do crystallographers think about these differences? So let's understand this in what we call a Miller indices pattern. So let's call about, this is the O, point O as the origin, and then A, B, C, D, E, F, and G. We are now looking at simple cubic system. Right? Now, the way we do this is, we can imagine infinite number of planes within the cube. For example, any three non-collinear points in the space define a plane, right? You can imagine a plane that has E, A, and C. Right, that's a plane. You can also say D, G, A, B, that's a plane. You can say G, F, C, B, this is a plane. So you can keep imagining. You can also draw a plane that cuts exactly in the middle of the plane like this. And you can create some additional points, like for example, M, N, O, P. That's another plane. Or you can also have a plane that cuts about 1/2 and create another plane. Now, the reason why these planes are important is because in different crystal structures, we encounter different atoms on different planes. So to solve the structures of the crystals, we need to understand a system through which we can define the planes within the unit cell and be able to assign a number. So according to Miller indices, any crystallographic plane in a solid can be represented by three integers called hk and l, small case. So you pick up any plane within the crystal, you can define a number hkl based on the intersection of that plane along the Cartesian axis. Okay, let us now try to talk about this. So let's take a plane within a cube. I have O, A, B, C, D, E, F, G. I just put the points here. Okay. Along the OA axis, I will call this y-axis. Along the OC, I call this x-axis. Along the OE, I'll call the z-axis. Okay, so the length OC is the cell dimension along A, x-axis, and along the Y, we call the axis length B, and along the z-axis, we say C. I'm now talking about an orthorhombic system where A, B, C are different lengths, and this is the Cartesian system. My origin for the three-dimensional geometry is O. Now let's imagine a plane that cuts the x-axis, y-axis, and the z-axis at 1/2 of the length. Okay, so we will now put some points P, Q, and R. These are the points, and I'll now join them to give you a plane. So what are the HKLs for the plane PQR? So when you look at the intercept, here it is OE divided by OP along the z-axis. So let's first talk about x-axis. So OC is the A, and this point is R, OR. And the other one is OC or OE, OE or OP. And then we have OA or OQ. If you now look at the fractional intercept, this is intercepting at 1/2. This is also intercepting at 1/2 of the distance, and that is also intercepting at 1/2 along the y-axis. So once you have the fractional intercepts, the only thing what you do is you take the inverse of these fractions. So this becomes 2, 2, 2, and that is exactly the HKL of the plane PQR. So we say it's 2, 2, 2 plane. 2, 2, 2 plane means it is intersecting the x-axis at 1/2 the distance, y-axis at 1/2 of the distance, and the z-axis at 1/2 of the distance. So you take the fractional coordinates and then take the inverse of the fractional coordinates to get to the HKL. So I'll give you a few more examples. But this is the idea we use to define the crystallographic planes or the Miller indices. So let's do 2 or more examples to make sure that we understand this. So instead of writing a cube, for the sake of clarity, I will just use the coordinate system. O, A, B, and C. This is your z-axis, x-axis, and y-axis. Okay, let's imagine a point which is 1/3. That is, if this total length is A, this point is 1/3 of that fraction. And let's imagine one more at 1/4 and the other one at 1/2. So if I were to draw a plane that intersects the z-axis at 1/2, y-axis at 1/4, and 1/3 along a-axis. So what will be its HKL indices? So we need to write down along the x-axis is 1/3, along the y is 1/4, along the z it is 1/2. These are the fractions. And the next thing that we do is we take the inverse of this, that becomes 3/4/2. So that will be the HKL of that plane.
Does the order matter?
Order, of course, matters because first we start with the x-axis, the next one is y, the next one is z.
Okay.
If you change that axis to 4, 3, 2, that's a different plane then. So when you say 4, 3, that's 1/3 along x-axis. But if this is 4, 3, 2, then it's 1/4 along the x-axis. So the order really matters. The h here corresponds to along the x-axis, the k is along y-axis, the l is along the z-axis. What if I have exactly at the same unit lengths? So this is the total length is A, B, and C. So the intercept is 1, 1, 1. So what's the inverse of 1, 1, 1? Same 1, 1, 1. So that plane is your 1, 1, 1 plane. We talked about 2, 2, 2 plane and 1, 1, 1 plane. Right? Let's talk about another type of planes, which the reason I'm giving so many examples is you can start seeing the similarities, and that makes your life a lot easier. So let's talk about another cube. The A, C, and B. That is along the y-axis. This is along the x-axis. That's along the z-axis. So that's the units of length here. Let's imagine a plane where you take these 2 points and then this plane here. So for the sake of clarity, let me put some points here. This is the origin. I'll just put only points here. A, let's not confuse with A, but let's put PQRs. P, Q, R, and S. So this is the plane we are now looking at, PQRS. So this plane is intersecting the x-axis exactly at A. So the ratio of intercept is 1 here. It is also intercepting the y-axis at 1, exactly at B. But is it intercepting C? That plane, as you can see, is parallel to the z-axis. Because a plane is parallel to the z-axis, theoretically, it can intercept only at a distance of infinity. But mathematically, we say nothing is impossible, right? I mean, they will, but that will be at infinite distance. Now, these are the intercepts. Now we take the inverse. Inverse of 1 is 1. Inverse of 1 is 1. What is inverse of infinity?
0.
0. So we say this plane has to be indexed as 1, 1, 0 plane. So whenever we have a 0, that L position is 0, which means this plane is parallel to the z-axis. If it is 0 in the middle position, it should be parallel to the y-axis. If it is 0 in the x-axis, it should be parallel to the x-axis. Am I making sense? Take one more example. Let's talk about another cube. That's my thing. So that's my origin. That length is A, this length is B, that length is C. I'm now trying to understand the plane PQRS. So that's the face of this cube here. What should be the indices for this? First of all, we need to know what fraction it is intercepting the X, Y, and Z axis. So if you look at the PQRS plane, that is intercepting the X-axis at a distance of A. So that ratio is 1. How about B and C? If you look at that face, isn't it true that this is parallel to both B and C? So in other words, it's now parallel to two different axes, so it should be infinity and infinity. So if you take the inverse of those fractions, that becomes 1, 0, 0. So this plane is your 1, 0, 0 plane. So if you look at this cube here, if you look at this side here of this cube, that is your 1, 0, 0 plane. Similarly, if you look at the top plane, that will be 0, 0, 1 plane. And this is also 0, 0, 1 plane. So these are all parallel planes. Am I making sense? So given any plane in the crystallographic system, you should be able to look at the fractional intercept of that plane along the each axis and take the fractions and invert those fractions and write down these numbers. That will be the Miller indices of any particular plane. Questions on this so far? So we will be using these Miller indices, especially the crystallographic planes. And I want you to keep in mind that this is a small unit cell that is isolated from the three-dimensional network. That means you have cubes above, below, on the left, on the right, in the front, and the back. So you have billions and trillions of cells like this. We are only looking at one cell in isolation. It's almost like a brick that is used to construct the walls and the buildings. We're trying to understand a brick. This is like a brick taken out from a three-dimensional network. And once we understand brick, because the rest of the unit cells are all the same, that's what the beauty of solid-state chemistry is. So in most publications, they look at the unit cell properties of solids, which is what we are trying to slowly introduce. The occupancies, the crystallographic planes, the densities, phase center, different type of crystallographic systems, and all that stuff. Any questions up to this point? Anything that's not clear? Okay, so in the next lecture, I will introduce the concept of X-ray diffraction. I'll be uploading a presentation on X-ray diffraction using the Miller indices. All right. So if there are no questions, we'll meet next Tuesday in person, but this Thursday will be recorded lectures. I'll be using a Kaltura program to record and then upload the lectures. Any questions? Okay, if there are no
Sounds good.
questions. Thank
Bye,
you very much.
Shari.